my talk is about time and how it matters. Namely, I come from the field of biophysics of living systems. And living systems all, as long as they are living, are dynamical systems. But not only that they are dynamical systems, their characteristic is that they're usually, even the simplest of the living systems, do not appear as a single mode system. And it's very difficult actually to reduce to single mode. So there are multi-mode, multi-scale systems. And moreover, there are continuously cycling. Almost there is no physical parameter related to living systems that you will not find it cyclic. If it is not cycling, possibly it's because the amplitude is low or towards zero. But definitely there are very often cyclic systems because life is actually connected to the daylight, to our intake of energy, and so on and so on. So cyclicity is ubiquitous in living systems, but it's complex because of multimodality. Yet, none of the living systems is perfect clock. So these are the ingredients that make us, or at least have been making me thinking about how best to describe living systems in physics and mathematical sense. Especially the fact that they are not strict clocks is very important. Actually, it's not only living systems of what we think of living system. Recently, news told us that even the Earth is not rotating perfectly clock-like. So there are plenty of cases where we have cyclic but not perfectly cyclic processes. So how to treat them in rigorous physics and mathematical terms is the question underlying my question, how the time matters. Because obviously, all these characteristics that I told you are very much indeed related with time. And I have been working in the field for long, and there are many collaborators that I have been working with and learning from various studies related to brain dynamics, related to cardiovascular dynamics, related recently also to cell energy metabolism dynamics. But this particular kind of lesson that I've learned, or I have been learning recently, is done in collaboration with Joe Rowland Adams, my PhD student, who I hope soon will no longer be PhD student, Julian Newman, who used to be my postdoc, and he's now postdoc with Peter Ashwin in Exeter, and myself. So just to tell you how broadly I have been thinking about the issues of how best to describe living systems, I'll go and briefly summarize what are the possibilities to date. We have the framework of deterministic dynamical systems, and as I said, living systems are dynamical, and dynamics is the study of motion of the various objects in the world around us. And most of the dynamics is still today very much under the theory of introduced by Newton long ago, who was studying the solar system indeed. And we all know that the three-body problem is not easy to solve, and Henri Poincaré showed that it is possible to derive the most important information about behavior of family of solutions without having to solve the equation by studying stability. And this was further enhanced or developed by the work of Alexander Lyapunov, very much at the same time as Henri Poincaré. And I would say if we are very broad and rough in terms of understanding the evolution of the theory of dynamical systems. Certainly, we can probably stop by 1963 with the work of Lorentz, whose work brought us to the field of chaotic dynamics and chaotic behavior. And this field of chaotic dynamics has been in various ways dominating the field of dynamical systems in the last almost 60 years. And one may be a little bit bold by saying, but yes, in general, for the case when the change happens monotonically, almost everything is known. And Newton's law specified the equation in detail. The results could be motion around a stable or unstable equilibrium point, or indefinite motion in a straight line. For the case of a multiple but still finite number of equilibrium points, the dynamics may be chaotic, as we just came here. And corresponding theory also has been, as I mentioned, for 60 years developed over the last several decades. But the question is this development bringing us to chaotic dynamics theory good enough solution for the question what is life, or how to treat life in physical sense? To my knowledge, maybe you can correct me, maybe at the end we can discuss about this, but I haven't come across to a really rigorous study pointing from data that there is dynamical behavior that is chaotic by nature, from data, from real measured data. So the other branch is mainly coming from physics. And this is based on the work by Einstein and Smoluchowski, who were trying to define what happens with the pollen grain on the top of some liquid where there are many, many molecules moving. So if we were discussing about deterministic dynamics with few modes, here we are entering the field where we deal with many, infinitely many, or a large number of interacting systems. And then this approach tells us that all can be treated in a probabilistic way, as random, and elaborated in terms mainly of statistical physics and mathematics. So the work of Einstein and Smoluchowski resulted in the theory of Brownian motion, and the difference between Brownian motion and white noise, where we talk about very many, is that in case of white noise, especially if we have uniformly distributed amplitudes and frequency, we have power spectrum density that is constant, while Brownian noise would have some slope. But in any case, the approach to many, when we have many interacting systems, is more of a probabilistic kind. So it cannot, however, distinguish between external driving and internal driving, because we all want to understand exactly what's going on by proposing models to be able to study, to gain the insight about the dynamics. So within this framework, it is generally irrelevant whether the motion is internally or externally driven. And the common feature of these approaches is that the motion is treated in a asymptotic limit of infinite time. But we want to understand life, and I haven't come across to anyone who is living infinitely long. And that's true for any dynamical process within any living systems. So what do we have as a possibility then? We have autonomous differential equations that are describing autonomous dynamical systems, where we have some change of the parameter that we are observing over time as a function or a certain function, where the function is of time, but the parameters are not function of time. And in physics terms, these non-autonomous dynamics differential equations would describe closed systems, thermodynamically closed, isolated from the environment. And in physics, we indeed have many models, many cases, many problems that can be treated in this way. And this approach is indeed very useful. But these systems incorporate no influence from external forces that can vary over time. And very often in living systems, I cannot remove the external forces. By removing food for a living system, I will make it die. So I need a theory, an approach where I can take into account the internal forces. And more realistic framework for many situations is non-autonomous differential equations. I would not go in the same way as I did for deterministic and stochastic dynamics with non-autonomous differential equation for various reasons. One is that it's relatively new and it's difficult to find out the pillars, but after some works in 60s, I would say, and lots of idleness in the field, the work of Peter Clodon, and especially afterwards also Martin Rasmussen, his PhD student, that resulted in the book Non-Autonomous Dynamical Systems, is particularly important for the field. And in brief, the difference being that we now have explicit dependence on time. Our parameters are time dependent. So, before I go and elaborate in a bit more detail, I shall tell you that if time is not taken explicitly into account, the behavior of such non-autonomous systems is most of the time today interpreted as a noise. In most of the cases that has been studied, you will find out very often non-autonomous dynamics interpreted as noise. And before I'm going to go into detail, I can show you, of course, if we are so much about time, then everything that we talk about in terms of dynamics should be evolved over time. And wavelets are very appropriate for this. And here, without showing you the equations, it's a very simple non-autonomous system with two modes, actually. I am showing you how this looks like seen through the eyes of a wavelet transform or seen through the eyes of Fourier transform, where time is not taken explicitly into account. And here you can see that we have quite a uniform distribution of the frequency peaks, pointing that there is certainly some kind of noise here. Instead, it's pure deterministic system with only two modes. So what I'm trying to understand is how best to explain the difference between isolated and non-isolated systems. And while we have, as I said at the beginning, classical framework for isolated system that probably solves most of the problems, maybe mathematicians would argue with me, because there are, of course, there are plenty of mathematical problems that are unsolved, but in terms of practitioner, if one works in the field of isolated systems, lots is available and done. But the framework when we have non-isolated system, where we have, for example, a pump, like we are pumped throughout our lives by daylight, by food intake, and so on. Whether we are aware of this or not, that's another issue. But this is true. Our heart is a pump for the whole body. There are plenty of pumps throughout the body. There are pumps in the cells, and so on and so on. So what happens when we have a case with many interacting systems and some kind of pump or many pumps as well? So for the isolated system, if we have many, as I said, we would usually consider this within statistical physics, maybe consider as classical Brownian motion, because this is indeed coming from the classical Brownian motion experiment. But for the force system represented by addition of time-varying pump, we, according to my opinion and experience over so many years, do not have appropriate neither mathematical tools nor a physical understanding of such systems. Of course, I should not stop stressing that the work of Clauden and Martin are very essential, but they are characterizing properties of non-autonomous systems, not providing further steps so that we can then develop this in terms of physical systems and descriptions. What happens because of this is that non-isolated systems are usually treated as autonomous. And the mathematical modeling assumption that a system can be described as autonomous differential equation represent physical assumption that the system can be treated either as entirely isolated from the rest of the universe, or at least as unable to have any interactions with the environment besides dissipation of energy into the environment. So the question then remains how to analyze non-isolated systems and time series result recorded from them. We need both to have good mathematical theory, good physics theory, and at the same time have all this at hand when we treat time series, and preferably have similar conclusions. Somebody mentioned that it's good to have a kind of not competition, but if we are all given time series, what will happen? Depends of what we can assume as possibility, I would answer. And I would really like to see this happening, especially if among the time series we have some kind of non-autonomous dynamics as well. So to treat systems where time explicitly plays a role and is explicitly taken into account, we propose kind of new framework. Of course, it's based on the existing theory of non-autonomous dynamical systems, but this new framework particularly has several pillars that we've learned are important over several years of work or several decades more. So first, physical systems in the real world are subject to ongoing external forcing will generally exhibit bounded, non-static behavior. Then the second point of this approach is that cyclic or oscillatory processes are within the system. In contrast to the classical model of cyclic processes as a stable limit cycle of an autonomous dynamical systems, these processes do not necessarily possess any internal strict periodicity, but instead progress through the cycle in a way that is inextricably linked to their ever-changing environment. And an important role of the functioning of a system is played by interactions between oscillatory processes within the system, and these interactions again can be time-dependent nature. And of course, noise is inevitable, and it still can be present, but what I'm arguing is that some of the noise actually is really not noise. Here, there is a very important point to take into account. And the fact that the oscillatory processes are cyclic but not strictly periodic implies that it is often appropriate to speak of time-localized frequency. And this can be done only as an approximate valued quantity. This leads to revisiting the concept of Heisenberg uncertainty principle. Because there is no possibility. We are talking about dependence on time, and we are talking about dynamics. This means that we are talking about movement over time. Yeah? And if the movement is not constant, the velocity of movement is not constant, then we really have to be very careful in considering the Heisenberg uncertainty principle. First of all, we have to evaluate the velocity of movement within certain window, but definitely there is no zero window within which we can evaluate. So we always make a kind of compromise between time localization and frequency resolution. But of course, as in classical quantum physics, also here, we can always have some guidelines how to optimize the two. So what is our mathematical framework? It's actually relatively simple. If we assume that the system's evolution can be modeled by a finite dimensional differential equation, we can express our physical description as follows. So we have a series as a function of angles between angles for each of the cyclic processes, plus some noise, plus maybe some other components. And the derivatives of the angles are explicitly time-dependent. So that then allows us to talk about the frequencies of these cyclic processes that are time-localized internal frequencies. And just for as an example here, we have a simple, very simple example for the function, just a sum of sine functions, and our frequencies can be distributed like in this form, where the coupling function can be any, but for the sake of simplicity, for example, in what I'm going to show you, with the examples I'm going to show you, we will have a Kuramoto type coupling function. So what happens most of the time when I talk about this and I come to here, most of the time I would have comments that, well, why do we need all these complications when we can express the time-dependent dynamics as additional parameter and treat the description as autonomous dynamical system. This is possible in very few cases, very specific few cases, but by far not possible in cases related to living systems, which are much more than a simple case that can allow this transformation to be possible. So the problem, why then we have a problem because of this common misconception, is that even outside such assumption on the time dependence, simply adding time itself as a new dimension in the phase space enables non-autonomous dynamical systems to be reduced to the domain of applicability of autonomous dynamical systems theory. But the problem with this is that the theory of autonomous dynamical system concerns bounded objects, like fixed points, periodic orbits, compact attractors, and so on, rather than being concerned with systems whose state grows unboundedly. Obviously, if time itself is regarded as part of the state of the system, then this state will grow unboundedly. And this has been nicely discussed by Peter and Martin in their book in 2011. So to illustrate what I want to tell you actually, I will show you first few numerical examples, and then I will move to real examples. And the numerical examples are of the form shown by the equation a few slides ago. So this simple example, and we will have case, for example, for autonomous case, we will have 10 oscillators or 100 oscillators or 10 to the power of 3 or 1,000 oscillators. And their frequency can be, in this case, there are distributed logarithmically, but they can be also linearly distributed or whichever way. So I'm trying to tell you that we have to have understanding both of how to describe the system and how to treat the resultant time series. Therefore, I will apply the most standard methods that are used today to characterize, for example, noise or dynamical systems of higher dimensions over the dimensionality where we usually assume maybe there is chaotic behavior and maybe we have to study features of chaotic behavior. And power spectrum density is most frequently used to calculate the noisiness of the signal, if you wish. And it's defined as a Fourier transform of the correlation or autocorrelation function obtained in this way. And noise is characterized by the exponent beta. If beta is 0, we talk about uncorrelated noise. If beta is between 0 and 2, we talk about pink noise or any other colored noise. And if beta is around 2, we talk about Brownian noise or Brownian motion. So with purely autonomous deterministic system, when I calculate power spectrum density and calculate the slope, note here that the slope is calculated such that every value of the spectrum is taken into account in the averaging process. And of course here the parameters play a role. What is the window size within which you calculate and what is the sampling frequency and so on and so on. But we have investigated quite systematically all these effects, and the maximum length we could afford for most of the cases I'm going to show you is being taken into account. And we end up, even in the cases where we have autonomous deterministic dynamics, but with larger number of components, we end up having to conclude that this is about noisy dynamics. Of course, only when we have fewer oscillators, like in this case 10, despite that the slope is showing some exponent that points to noisiness, we can always think that, okay, it's a noise, but also there are some characteristic peaks. As soon as we have more of these peaks, then this inevitably results in conclusion that there is noise. If we evolved the frequency distribution over time, we can see in what we obtained from the wavelet transform that we indeed have a relatively deterministic case. The numbers can be distinguished for quite a while, and not surprisingly, if we don't pay particular attention, I can assure you that with good investigation, with good resolution here, I can probably infer that there are thousands of oscillators or frequencies present there. When we have non-autonomous case, the situation is similar. The only difference being that we don't have any particular peak visible in the power spectrum density, so we inevitably are faced to conclude that this all is pure noise. In reality, I repeat again, these are just simple non-autonomous dynamical systems of various order. Here, even just only 5, but we have no way to say that 5 means determinism if we were applying power spectrum density only. We can even go with a single one of this kind when we have a periodic modulation of the frequency, and again conclude wrongly that there is noise. One can go on and study various situations, like in this case, we have up to now, when we studied non-autonomous cases, here, and in this picture we did not have any coupling. Coupling was 0, but we can play, for example, here again there is no coupling, but we can play with the coupling, and by increasing coupling we can observe what's going on. If we were calculating power spectrum density, we would have in all cases concluded that there is some kind of noise resulting in the time series that we are observing. But if we were analyzing time frequency, we can see that there are many. Just for your information, here in this case we have intermittent synchronization. I will not go into this detail. We have been quite systematically investigating properties of this kind of systems. Very interesting, just as a side conclusion, is that when we have non-autonomicity, and this is shown in this picture here, this is a case of non-coupling present, so autonomous system, and here we have non-autonomous system. We have kind of widening of the Arnold tongue, meaning that non-autonomicity in some way extends the parametric space of stability of the system. So most of this is on account of intermittent synchronization, and I needed to tell you this because indeed this is a case with intermittent synchronization, which we can study immediately by trying to find out couplings. I'm sure Tomislav will be telling us about couplings using Bayesian inference method. Here we study couplings using bispectral, wavelet bispectral method, no matter which way you study. If you were going the way when time is included, you can investigate if coupling is present, like here. In this case, there is no coupling, or here when we have some coupling, or here when the coupling leads to synchronization. That's why we have just a single oscillation appearing here, but we can investigate this and find out by studying couplings. So if we went the route of studying time-evolved dynamics and assuming that there are couplings, we can unwind all sorts of properties of these systems. If we were going with just statistical physics approach, in each of these conditions we would only conclude there is noise. Another way of studying this kind of complex systems, as networks would be for sure, is to evaluate some parameter related to complexity. We have been discussing yesterday at least about entropy measures, and one of these measures is multi-scale sampling entropy, but one can probably apply other algorithms as well. And here we have applied multi-scale sample entropy for the case A and B of autonomous oscillators, 10, 100, or 1,000, or non-autonomous oscillators, 5, 10, or 100, so much less than here. And when we don't add any randomness for this algorithm, we have one picture, but the algorithm by definition works better if there is some additional randomness. So this is what we have added here, and we see that in both cases, just by calculating a multi-scale entropy, we can conclude that there is no difference between autonomous and non-autonomous dynamics. But in reality, there is a significant difference between the two. Similarly, autocorrelation measures, again, I only pick up autocorrelation. We can go and investigate many more, are used very frequently to study whether there is any memory in the system. And again, we don't learn significantly much insight by just applying autocorrelation on this numerically generated data. I would like now to show you several examples of real world, just to discuss once again how much possibility we have in case we have taken into account the time explicitly or we haven't. So the first example is from the river Lune in Lancaster, where I come from. River Lune is very essential for the life in Lancaster. It marks the life very much because Lancaster is almost where Lune comes into the sea, and we have about 6 to 10 meters tides. So the water is, the amount of water is fluctuating quite significantly. And here is a recording for about 10 days, sometimes I think in February this year. The fact that they look a little bit strange is just because the sensor is put at 2.5 meters, if I'm not mistaken, or 2 meters, 2.15 meters. Therefore, everything below 2 meters will not be recorded. But this is just for your information. It's not essential for what we want to understand from the data. So if we just analyze this time series using power spectrum density, we will end up concluding with the beta that, again, that there is some kind of noise. The entropy measure will also tell us that there is some kind of entropy. Obviously, the window within which the entropy is calculated determines the magnitude of this entropy, and we obviously didn't have long enough to find out whether there is convergence here. But my point is, we won't be able to learn much about the insight, about the physics of what's going on behind this time series. If we applied wavelet transform, what we can do is we can see 3 interesting modes, which are all, their frequencies are not actually relatively, compared to living systems, are relatively constant, but not superbly constant. We also observe amplitude modulation. And next we can do is we can extract the phases of these frequencies and find out couplings and so on, or we can apply coupling analysis already in the amplitude functions. And as you can see here, from these 2 points, there is indeed some signature of coupling.
Is it from the signal or
Yes. Yes, there is a peak. There is a peak, but because of the shape of the signal. Yeah. Absolutely. I can give you the data and you can play if you wish. This is what you get indeed. There is a peak, it's here, but because of the shape of the signal, you have immediately, and as I said, you may end up wishing to conclude, okay, there is some small peak here, maybe there is periodicity, maybe not, and so on and so on. But if you just calculated power spectrum density, as I said, just as a slope of the power of the frequency spectrum as it is, this is the slope you will get. Okay? So what I'm trying to say is if time is taken into account, I can immediately know that there are 3 potential physical processes that are making up the signal that I measured. They may be just harmonics, and we have developed methods to detect harmonics of non-constant frequencies. Because harmonics, when the frequency is constant, is relatively easy to detect, but when the frequency starts varying, the second, third, and fourth harmonic are varying as well. So you need mathematical rigor to exactly determine. But this is doable. What I want to say is, once we see the modes, we ask, are they independent, dependent? Are they coupled, uncoupled, and so on, and gain enormous amount of physical insight into what is contributing to the signal we are measuring. I have another example. Okay, maybe I can skip because it's similar to this one. It's a height of water in Cooker's Dyke River. There they have pump. It's a little bit more complex than this. They have pump to prevent flooding, continuously pumping the water, so it's more complicated than the case I showed you. But again, if I applied power spectrum density, I would have ended up concluding that there is kind of noise, whichever color of noise. And also the entropy measure would not tell me much, some kind of quantification, but not an insight into the physics of the system. Again, if I evolve this over time, I can see that there are some periodic with varying frequency modes present there. I can again ask question how independent or dependent they are, and I can again ask question how coupled or uncoupled they are. Similarly, we have another example from physics, ionospheric magnetic field. This signal is even more complicated, but again, we can easily see that there are some modes present there. If we did power spectrum density, we would have concluded some kind of noise. If we did entropy measure, we would have concluded some level of complexity, but no physical insight. And here, immediately we see that there is clear coupling. So there are processes, underlying processes that are coupled. And we can further investigate what is the physics of this coupling, what makes this, and go and gain insight into the process of generation of ionospheric magnetic field. So I will summarize at this point by saying that without the need either for very large n, so very complex system, or for chaotic behavior, or for fast time scales, the incorporation of time dependence, especially in any model, not necessarily of fast time scales, can lead to the result that a typical PSD approach will characterize as noise. For analysis of experimental time series data arising from a system where our framework is appropriate, a different methodology is needed, and I would say different mathematics and different physics is needed to distinguish prominent functionally important oscillatory components from noise. As to methods for time series analysis of non-autonomous case, we have been working for over years. We have actually developed log normal type of wavelet, just wishing to particularly optimize the trade-off between frequency and time. We have also proposed our own algorithm of wavelet phase coherence. We can do ridge extraction. Wavelet bispectral analysis can be used for coupling or dynamical Bayesian inference. As I said, I'm sure Tomislav will be telling you more. And I would like to, thank many colleagues, particularly that were involved in discussing this part of the work. And I'm thanking the source of the data that I used, the real data that we used for analysis, and some of the funding bodies that supported this particular work. I have written thank you for your attention. I'm not sure where we are with time because I have some more to tell you.
We do actually about 4 minutes.
4 minutes. I'll try my best because I. 5. Okay. I want to kind of tell you how this matters. So first of all, I hope I managed to convince you that time matters, but how it matters. In both, in modeling approaches and also in analysis. I think for analysis, I told you quite a lot, but for the modeling, let me show you briefly. One of the things we want to understand is how cell produces its energy, because when we are talking about the difference between living systems and non-living systems, the main difference is that living systems themselves, I cannot say produce, they don't produce, but they themselves contribute to preparation of the energy they need for their functioning. Contrary to non-living systems where energy is available, or it's not available, but is available in some way. So very important is to understand how this energy generation happens in living systems at the level of single cell. Because I'm not sure whether you are aware, but all of us produce an equivalent of our body weight of DNA in 24 hours. So it's a huge machinery that is very little understood by now. And this machinery is basically made of two branches. One branch is glucose-based production of the ATP, and the other branch is oxygen-based production of ATP. About 28 molecules of ATP are produced in each cycle by mitochondria using oxygen, and about 2 molecules of ATP are produced by glycolysis from glucose. But these 2 molecules are needed for this cycle, so it's not only that sometimes our metabolism will change and become more of glycolytic type than of oxygenation type, and various diseases may come, like I have mentioned somewhere here, cancer and even many other diseases. So what we can do today is we can measure NADH, one of the products of this glycolysis part of ATP production. And one possibility is to go traditional method and apply kinetic model. So this is how the experiment works. They kind of detach the other branch so that they have simple kind of model. And if each of these chemicals that are involved in production are represented by equations of using kinetic model. And at the end, we have 22 input parameters and 7 governing equations. For those of you who want to see this, I see that in this, oh yes, Amemiya et al., it's a paper in Chaos from 2019. So, first of all, it's only one of the branches, and it's 22 input parameters has 7 equations. And this is how the NADH is measured. This is what the model can produce, and these are the time frequency representation. In a way, similar, but quite far away from being realistic. We have used a non-autonomous approach with networks of non-autonomous oscillators, and we have attempted to model both branches, both the glycolysis and the oxidative branch, and we have ended up, so you have couplings that represent how efficient the glucose is delivered and used in this branch, how efficient oxygen is delivered and used in this branch, and how these 2 branches communicate with each other. And the network is then used to represent glycolysis oscillators and mitochondrial oscillators, because on average in each cell we have of the order of 500 mitochondria. And using non-autonomous approach, we ended up with 21 experimentally measurable inputs, because when you have continuous exchange of energy and matter, measuring parameters is not an easy task, because everything is continuously changing. What we measure and what we model in this case are frequencies and phases, which are very easy to model. So we have 21 experimentally measurable input parameters and only 2 governing equations, and plenty of opportunity because we have network and we can really study all sorts of changes. Some here tried even to think about how metabolism changes due to COVID at this level. So, and this is the time frequency representation of the time series that are generated in this way compared to the real measured data. And maybe I should only say that 21 experimentally measurable input parameters and 2 governing equations for both branches compared to the equations only for one of the 2 branches before. So, in terms of modeling, it's different approach, but I believe it is giving enormous flexibility and possibility for exploration, the physical properties of the system, not only just parametric modeling of measured values. And the last I wanted to say is, in terms of analysis, I think I showed you benefits of this approach, but one of the areas where we applied it is in multi-scale time result analysis of circadian rhythms after the clocks in the brain, the genes were removed, and mice were put 24 hours in dark, meaning that all what they call canonical pace givers were removed. And the question was, what remains? And if we were studying using traditional approach, nothing remains. If you smash this without time, you don't find anything but kind of noise. And we have found out that there are 4 remaining modes that stay, not 24 hours. The 24-hour is gone. In here we can see it changes to around different mice in different way, but between 15 and 20 hours. And then there are slower ones, which we are now in collaboration with Shin Yamazaki from Dallas. We are trying to find out what is the biological origin. So that's all I wanted to say. Especially, I wanted to show this example because I was impressed by the campus, and I checked who is the chancellor, and the chancellor is studying of this university, seems to be studying circadian rhythms and has contributed significantly. So I was interested to see. So let me just finish by saying, how do I see living systems as networks of oscillators of non-autonomous kind. At cellular level, as I showed you, we can have microscopic description of the system. At organ level, so each of these unit will be part of the organ level, a mesoscopic description, and each of these units will be part of our system level at the macroscopic description. So this is just as an outlook where all this, which I told you, might one day be useful. Thank you very much for your attention.